This story is about a planet that refuses to fit our familiar frameworks. A world where ordinary words lose their earthly meaning, where intuition ceases to be a reliable guide. A body we have seen up close only once, and since then have only guessed at what is truly happening there. Not a sensation, not a legend, a calm, unhurried conversation about a planet that exists at the very edge of our understanding. Imagine a world that rotates lying on its side, as though someone once pushed it and forgot to straighten it back up. A world where a year lasts longer than a human lifetime, and polar night endures for decades. A world where water, compressed by enormous pressure, becomes an electrical conductor, and the magnetic field does not emerge from the center as it does on Earth. It is offset, tilted, and constantly shifting shape, like a living shield. Rings that do not reflect light. Moons, among which one appears to have been shattered and pieced back together from its own fragments. An atmosphere that looks calm, but conceals winds that accelerate against the very rotation of the planet. And perhaps strangest of all, the near total silence of the depths. This planet radiates almost no heat of its own, as though it cooled more deeply than all the others, and has been concealing it ever since. What do we actually know about it? Almost everything we have comes from a single brief flyby of one spacecraft and decades of observations from a distance. What matters more when it comes to a planet at the very frontier of our knowledge? Confidence in what we have already described, or honesty about what we still do not understand? If you had one brief chance to draw close to such a world, how would you spend it? On answers or on new questions? Listen, this story is about a planet that holds its answers at arm's length and offers them up without hurry. Uranus occupies a singular place in the solar system. It cannot be classified among the rocky terrestrial bodies, nor among the true gas giants like Jupiter or Saturn. Scientific literature places it in the category of ice giants, though this term is easy to misunderstand. We are not talking about ordinary solid ice, but about the interior composition of the planet, dominated by water, ammonia, and methane in states far removed from anything familiar to earthly experience. Already this makes Uranus an object that resists intuitive notions of what a planet is, and one that demands a slow, attentive examination. The discovery of Uranus was a turning point in the history of astronomy. Until that moment, the solar system was considered to be bounded by 6 planets, those visible to the naked eye. Uranus was found with a telescope, and this event changed the very understanding of how scientific knowledge can expand. The planet was too faint for ancient observers, though it appeared in certain star catalogs as a fixed point that aroused no suspicion. Only systematic observation and analysis of that point's motion made it clear. This was not a star, but a large body orbiting the Sun. Uranus's position in the solar system determines many of its characteristics. It orbits at a distance at which sunlight is already noticeably weakened, and the planet's energy balance is strikingly different from that of the inner planets. The heat received from the Sun is small, and this affects the temperature of the upper atmospheric layers, the behavior of clouds, and the nature of chemical processes. At the same time, Uranus radiates almost no heat of its own, and this distinguishes it even among the ice giants. Observations indicate that its internal heat flux is significantly weaker than Neptune's, despite the two planets being very similar in mass and size. Before going deeper, it is worth understanding how Uranus exists in time. For one of its years lasts longer than a human life. Uranus's orbital journey around the Sun spans several decades. Over this time, extremely slow seasonal changes unfold on the planet. One complete revolution is comparable in length to a human lifetime, and the changing of seasons stretches across a decade. This timescale makes Uranus an exceptionally difficult object to study. No single scientist can follow a complete Uranian year within a single scientific career, and data must be passed down between generations of observers. The history of studying Uranus is inseparable from the development of observational instruments. Ground-based telescopes remain for decades the primary source of information about the planet, enabling the first measurements of its size, mass, and orbit. Later, spectroscopy revealed the composition of its atmosphere and the presence of methane, which absorbs the red portion of the spectrum and gives the planet its distinctive blue-green hue. Nevertheless, for a long time Uranus remained merely a disk against a field of stars, with no distinguishable structures or phenomena accessible to direct analysis. This changed with a single spacecraft that has ever flown close to the planet. In a limited window of time, it transmitted data on the magnetic field, the rings, the moons, and the structure of the atmosphere. Science received a detailed snapshot of the system's state, but not a full film of its evolution. In the context of planetary science, Uranus is often viewed as a key to understanding the processes by which bodies form beyond Saturn's orbit. Contemporary models suggest that ice giants coalesced under conditions where volatile compounds played a decisive role, and where the gas envelope never reached the scale of Jovian giants. Observations of exoplanets confirm that objects similar in characteristics to Uranus and Neptune are among the most common in the galaxy, and this gives the study of Uranus a significance that reaches far beyond the solar system. What is hidden inside this unhurried giant? Its mass and density already hint that something unusual is happening there. Uranus ranks among the large planets of the solar system, yet its physical characteristics do not immediately correspond to what we see from the outside. Its diameter greatly exceeds Earth's, but falls well short of Jupiter's and Saturn's. The planet's mass is several dozen times that of Earth, which immediately points to fundamentally different conditions of pressure and gravity in its interior. Its average density, however, remains relatively low, indicating a predominance of light and medium-weight compounds rather than the iron and silicates characteristic of terrestrial planets. Uranus's gravitational field has been studied in considerable detail through observations of its moon's motions and the trajectory of the spacecraft that flew past it. These data allow the total mass and distribution of matter in the deep layers to be determined with reasonable accuracy. The detailed picture of the internal structure, however, remains an area of modeling, since direct measurements are inaccessible. The most widely accepted model describes a three-layer structure. At the center, a comparatively small rocky core of heavy elements, estimated in mass at several Earths. Above it, a vast layer of so-called ices, meaning not solid crystals, but dense fluids of water, ammonia, and methane under extreme pressures. And finally, the outer layer, an atmosphere composed primarily of hydrogen and helium with an admixture of methane. It is important to understand that the boundaries between these layers are in all likelihood not sharp. Contemporary models allow for gradual transitions, where composition and physical properties change smoothly rather than abruptly. This complicates the interpretation of data, since different models with different density profiles can explain the observed gravitational field equally convincingly. Uranus's internal temperature regime is of particular interest. Despite its considerable mass, the planet radiates into space only a negligible amount of heat beyond what it receives from the sun. This means that the internal energy source is either weak or reliably insulated from the surface. For comparison, Neptune, similar in size, demonstrates a noticeably higher internal heat flux, and the reasons for this difference are not yet fully understood. Gravity at the level of Uranus's upper cloud deck is only slightly less than Earth's, a fact that often surprises people since the planet is several dozen times heavier than Earth. The explanation lies in its large radius. Surface gravity is determined not only by mass, but by distance from the center. As a result, conditions in the upper atmospheric layers turn out to be comparatively moderate by this measure, even though pressure and temperature rise rapidly as one descends deeper. We are at the very surface of the atmosphere, and now it is worth understanding what it consists of and why it has the color it does. Uranus's atmosphere is the most accessible layer of the planet for observation, but its apparent simplicity is deceptive. At first glance, it appears uniform and comparatively calm, especially compared with the turbulent cloud structures of Jupiter or Saturn. Nevertheless, spectral measurements and long-term observations reveal a complex chemical composition and a subtle vertical structure in which physical processes unfold slowly and often out of sight. The foundation of the atmosphere is hydrogen and helium, dominant by mass and volume, forming a thin, gaseous envelope that gradually densifies with depth. Methane plays an important role, though its proportion compared with hydrogen is small. It is methane that determines the optical properties of the atmosphere. It efficiently absorbs the red and infrared portions of solar radiation, shifting the reflected light toward the blue and greenish range. The blue color of Uranus is not water and not sky. It is methane molecules absorbing red light, and in that sense it represents a kind of chemical signature of the planet. The distribution of methane in the atmosphere is uneven. Its concentration varies with both latitude and altitude. In equatorial regions, there is generally more methane than in polar regions. The reasons for this distribution are not yet fully understood, though there is a hypothesis linking it to global atmospheric circulation, in which gas rises at certain latitudes and descends at others, transporting methane and altering its vertical profile. The temperature of Uranus's upper atmospheric layers remains one of the lowest among solar system planets. In the troposphere and stratosphere, extremely cold conditions have been recorded, under which most familiar terrestrial gases would exist in a condensed state. At the same time, temperature does not decrease monotonically with altitude. In the upper layers, warming has been observed, associated with the absorption of solar radiation and interaction with the magnetosphere. But the mechanisms of this heating have so far been only partially described. Uranus's cloud structures remained nearly indistinguishable for a long time. Only with the development of adaptive optics and infrared observation did it become possible to detect individual clouds, bands, and vortices, formations consisting probably of methane ice crystals and other condensed compounds. Wind speeds on Uranus can reach considerable velocities, and at certain latitudes they exceed the speed of the planet's own rotation and flow in opposite directions in the two hemispheres. This asymmetry points to a complex circulation that depends on depth, latitude, and seasonal factors. Since one season on Uranus lasts many years, changes in atmospheric dynamics occur extremely slowly and require long observational series to detect. Atmospheric chemistry is not limited to simple light gases. Under the action of solar ultraviolet radiation, methane breaks down to form more complex hydrocarbons, which can create a thin haze in the upper atmosphere, affecting the heat balance and optical properties. The composition and distribution of these photochemical products remain an area of active research, since direct measurements are difficult. Uranus's rotation axis is tilted in such a way that the entire atmosphere, climate, and seasons operate completely differently from any other planet. One of the most unusual features of Uranus is the orientation of its rotation axis. Unlike most planets in the solar system, it is tilted almost at a right angle to the orbital plane, so the planet rotates as though lying on its side. Its poles alternate in being pointed almost directly at the sun. On Uranus, polar day lasts not months, but long years, and an equally endless night awaits the other pole, until the situation gradually reverses. The reasons for such an extreme tilt remain a subject of scientific debate. The most widespread hypothesis links it to a large collision in the early stages of the planet's formation. Uranus may have interacted with a massive protoplanetary body whose impact changed the orientation of the axis without destroying the planet. Alternative proposals involve a series of smaller collisions or gravitational interaction with a surrounding disk of material. Direct evidence in favor of any specific scenario has not yet been found, and each model has its own limitations. The duration of seasons on Uranus is measured in decades, and the atmosphere responds to changes in illumination extremely slowly. Unlike Earth's atmosphere, where temperature contrasts between summer and winter are quickly smoothed by active circulation, on Uranus, energy imbalances can persist for a long time. Observations show that temperature differences between hemispheres exist, but they do not always match simple expectations based solely on the amount of sunlight received. This points to the existence of efficient mechanisms for redistributing energy, or to high thermal inertia in the planet's upper layers, which smooth out the contrasts. Despite years of continuous illumination of the poles, no significant overheating of the polar regions compared with equatorial ones has been observed. Possible explanations include horizontal heat transfer, complex circulation, and the influence of the deep layers. Seasonal changes are reflected in both cloud structure and wind dynamics. Long-term observations show that atmospheric activity can increase near equinoxes, when illumination becomes more even. During these periods, new cloud formations appear, and contrasts intensify in the infrared range. But such conclusions are based on data covering only part of a Uranian year. The tilt of the axis also affects the magnetosphere. Since the magnetic axis is also strongly tilted and offset from the planet's center, the interaction with the solar wind changes depending on Uranus's position in its orbit. In different seasons, the magnetosphere's configuration can differ substantially, affecting the fluxes of charged particles and the energy exchange with the upper atmospheric layers. This tilt could not help but affect the magnetic field, and it turned out to be even stranger than might have been expected. Uranus's magnetic field is among the most atypical in the solar system. Its structure and orientation differ markedly from what is observed at Earth, Jupiter, or Saturn. The first data on it were obtained only at the moment of a spacecraft's flyby of the planet, and even then it was clear that familiar notions of planetary magnetospheres applied here only partially. Uranus's magnetic axis is tilted by dozens of degrees relative to the rotation axis, and the magnetic dipole itself is noticeably offset from the planet's geometric center. As a result, the field near Uranus is asymmetric, and its intensity varies substantially across different regions. Uranus's magnetosphere changes shape and orientation with each rotation of the planet, as though the protective shield is in constant motion. Unlike Earth, where the magnetic field creates a comparatively stable, protective cocoon, Uranus's magnetosphere undergoes strong deformations. The structure of the bow shock, the magnetopause, and the magnetospheric tail can change sharply even within a single rotation. The source of Uranus's magnetic field, according to current understanding, lies not in a metallic core, as on Earth, but in a layer of electrically conducting fluid composed of water, ammonia, and other compounds in unusual phase states. Under high pressures, these substances are capable of conducting electric current, and their motion, in combination with the planet's rotation, generates a magnetic field. If the dynamo zone is located not at the center of the planet, but closer to the surface, the resulting field will differ from a symmetric dipole, which accords well with observations, though direct data on deep processes remain unavailable. The interaction of the magnetic field with the solar wind has a number of unusual consequences. At certain times, the field may be oriented such that the solar wind penetrates more deeply into the planet's vicinity. At others, a more extended magnetic tail forms, creating a complex and variable distribution of charged particles. Uranus's magnetosphere contains radiation belts of high-energy particles, whose structure differs from Earth's belts and is linked probably to the unusual geometry of the field. These belts influence the atmosphere and the planet's moons, causing ionization of gases and changes in the surface layers of icy bodies. Auroras on Uranus have been detected only episodically and exclusively in the ultraviolet range. The planet's remoteness and the faintness of these displays make observation extremely difficult. Nevertheless, the available data confirm that the magnetic field guides charged particles toward the upper atmospheric layers, where they interact with gases and produce emission. The location of these auroras differs from Earth's and reflects the complex configuration of the magnetosphere. Moving from the invisible field to what is visible around the planet, there too is something remarkable: rings that barely reflect light. Uranus's ring system remained unknown for a long time, even though the planet itself was discovered long before the advent of modern astronomy. Unlike the bright, extensive rings of Saturn, Uranus's rings reflect almost no sunlight. They were not found by eye or through an eyepiece. They were discovered by the way they extinguish the light of distant stars, the occultation method, rather than direct visual observation. This alone points to the specific physical properties and composition of the ring system. Uranus's rings form a narrow and compact system of several distinct structures, located in the planet's equatorial plane. Each ring has clearly defined boundaries, and the gaps between them are nearly free of any appreciable amount of material. This structure distinguishes Uranian rings from the more diffuse systems of other planets. The ring material consists predominantly of comparatively large particles, which can reach meter-scale sizes, meaning there is little fine, light-scattering dust in the system. This is precisely why the rings appear dark and difficult to distinguish. Spectral observations point to the low albedo of the particles, which may be associated with the presence of organic compounds or processed ice subjected to prolonged radiation exposure. The dynamics of the rings are closely linked to the presence of so-called shepherd moons, small bodies moving near the rings and confining particles to narrow limits through gravitational influence. Observations confirm the existence of such moons near certain rings, though for all structures their role has not been unambiguously established, leaving open the question of the mechanisms that maintain the entire system's sharp structure. The origin of the rings remains a subject of debate. One proposal posits the disruption of a small moon by tidal forces. Another views the rings as remnants of material that did not become incorporated into moons during the early stages of the system's formation. Neither option allows for a definitive choice. The long-term stability of the rings is a separate, important topic. Theoretical calculations show that without additional mechanisms, the rings should gradually spread or break apart under the action of collisions and gravitational perturbations. The existence of narrow, sharply defined rings indicates either that they are relatively young or that dynamic processes exist to compensate for material loss. The interaction of the rings with Uranus's magnetosphere, charged particles gradually altering the chemical composition and reflectivity of ring particles, has so far been only partially studied, although such processes are well known at other planets. Around Uranus, there are not only rings, but an entire family of moons with remarkably different histories. Several dozen known moons orbit Uranus, differing noticeably in size, shape, composition, and geological history. These bodies do not form a single, uniform family. Each large moon displays its own set of characteristics, making the system as a whole a valuable source of information about the processes of formation and evolution of planetary systems. Uranus's largest moons consist predominantly of a mixture of water ice and rocky material. Their average density indicates that the fraction of ice in them is considerable, though the presence of denser inner layers is not excluded. The surfaces of these bodies are for the most part cold and ancient, yet on some of them structures have been found that speak to a complex geological history: faults, canyons, signs of surface reworking that arose, apparently, as a result of internal activity or external impacts. Of particular interest is Miranda, a small moon whose surface is remarkable for sharp relief contrasts. Ancient, heavily cratered regions sit alongside comparatively young areas with a network of grooves and scarps. This combination long provoked debate. Some models propose that Miranda underwent a period of internal heating associated with tidal interactions, while others admit the possibility that the moon was disrupted and reassembled in the past. Neither hypothesis has received final confirmation. The larger moons, Ario and Titania, show signs of tectonic activity. On their surfaces, there are extensive valleys and faults that formed, probably, as a result of expansion of internal material during freezing or under tidal forces in the system's early history. These structures suggest that even in the cold conditions of the outer solar system, processes capable of reshaping surfaces on geological timescales are possible. Oberon, by contrast, appears calm and ancient. Its surface is densely pitted with impact craters, and signs of tectonic activity are far less pronounced. This may indicate differences in the thermal history of the moons, even those that formed from similar material. The reasons for such differences are not fully understood and may relate to initial conditions of formation, as well as subsequent gravitational interaction with the planet and other moons. Uranus's small moons constitute a separate category. Many of them have irregular shapes and sizes comparable to large asteroids. Their orbits are often closely linked to the ring system, and some of them probably participate in maintaining its structure. Under the strong gravitational influence of the planet and neighboring moons, the orbital dynamics of these bodies may turn out to be unstable over long timescales. The chemical composition of moon surfaces is also of interest. Spectral observations reveal the presence of water ice and dark components, probably containing complex organic compounds. Under the influence of radiation and micrometeorite impacts, the surface gradually darkens and alters its properties. These processes unfold slowly, but over timescales of billions of years, they substantially change the appearance of the moons. What happens even deeper, in the very interior of Uranus, where pressure turns water into an electrical conductor. Uranus's internal structure remains one of the least studied areas of planetary science. The deep layers are inaccessible to direct observation, and all conclusions about them are built on indirect data: the planet's mass, its shape, rotation features, gravitational field, and the behavior of its magnetic field. The totality of these parameters allows physical models to be constructed, but each of them contains assumptions and areas of uncertainty. Beneath Uranus's comparatively thin atmosphere lies a vast shell of dense fluids, composed predominantly of water, ammonia, and methane. These substances are conventionally called ices, but under Uranian conditions, they are not in a solid state. In the planet's interior, pressure and temperature are so high that familiar phases of matter cease to exist. Water can enter states combining properties of liquid and solid, as well as forms with high electrical conductivity. Inside Uranus, water becomes an electrical conductor. This is not a metaphor, it is physics, at pressures of millions of atmospheres. One of the key questions concerns energy transport inside the planet. In classical models, heat from the depths rises to the surface through convection, but Uranus shows a weak heat output, indicating suppressed or inefficient convection. There is a hypothesis that stable layers with different chemical compositions have formed inside the planet, impeding vertical mixing and retaining heat at depth. Alternative models consider the peculiarities of chemical composition and phase transitions inside the icy layer, which can also suppress energy transport. Chemical stratification may also play an important role in the formation of the magnetic field. If the electrically conducting layer is positioned asymmetrically and does not encompass the entire planet, the generated field will be offset and complex in form, which accords well with the observed features of Uranus's magnetosphere. In this way, data on the magnetic field become an indirect tool for studying the planet's interior structure. Temperature estimates for the internal layers differ substantially between models. Uranus's heat flux is small and difficult to measure. Under certain pressures, exotic states of matter arise, actively studied in laboratory experiments using shock waves and powerful lasers. The results of these experiments are gradually refining models of Uranus's interior, but a direct correspondence has not yet been achieved. The structure of the central core also remains uncertain. Some calculations allow for a comparatively compact core, others for a more diffuse one that gradually merges into surrounding layers. And these differences significantly affect the interpretation of the planet's evolution. Almost everything we know about Uranus was obtained by indirect methods, and this in itself speaks to the limits of our knowledge. Knowledge about Uranus has accumulated unevenly and depends in large part on a limited number of observational approaches. Unlike Mars or Jupiter, which are studied by means of multiple orbital spacecraft and landing missions, Uranus has been the object of close investigation only once. All other understanding of the planet is based on remote methods, each of which has both strengths and limitations. Ground-based telescopes remain for decades the primary source of information about Uranus. With their aid, orbital parameters, rotation rate, overall brightness, and spectral changes were determined. The development of spectroscopy made it possible to identify the atmospheric composition and estimate the distribution of methane and other components. However, because of the planet's great distance, the spatial resolution of such observations remained low for a long time, and many details were blurred or went entirely unnoticed. Substantial progress came with adaptive optics in infrared observation. They made it possible to distinguish cloud structures, track their evolution, and measure wind speeds. Nevertheless, such data cover only limited time intervals and do not allow confident statements about long-term trends, particularly given Uranus's extremely slow seasonal cycles. The single, close flyby of Uranus yielded fundamental data, yet all that information relates to one specific moment in the planet's history and does not reflect its variation over time. Many parameters, heat balance, magnetospheric dynamics, may have been in a particular state during that period, not necessarily typical of other epochs. After that flyby, research on Uranus returned to remote observation. Space telescopes operating outside Earth's atmosphere expanded the possibilities of spectral analysis and refined temperature profiles, but even they cannot penetrate deep into the atmosphere or provide direct information about internal structure. A serious limitation remains the absence of data on the temporal variability of many processes. Uranus's heat flux has been measured with great uncertainty, and its possible changes over the course of an orbital period are virtually unstudied. An analogous situation exists with the magnetic field. Its configuration is known to be complex, but how stable it is over time and how it changes over timescales of decades remains an open question. Moon surfaces have been studied unevenly, and small moons and ring details are often at the edge of instruments' resolving capabilities. Uranus is one of the most common types of planet in the galaxy, yet at the same time, one of the least studied in our own solar system. Exoplanet observations show that objects comparable in characteristics to Uranus and Neptune occur far more frequently than massive gas giants or terrestrial worlds. Spectral data from distant planets are often interpreted through the lens of models based on Uranian and Neptunian analogs, which means that the incompleteness of knowledge about Uranus directly affects the interpretation of observations beyond the solar system. In this context, Uranus becomes not only an object of study, but a reference point for broader conclusions about the nature of planetary systems. The unresolved questions surrounding Uranus span virtually every level of its structure. The precise composition and structure of its interior layers remain unclear, as do the nature of matter's phase transitions and the degree of chemical stratification. It is not fully understood why the planet radiates so little heat of its own, or what processes determine its thermal evolution. The magnetic field, described in broad outline, requires refinement in terms of its temporal variability and its deep-seated source. The atmosphere, appearing calm, conceals processes that have not yet been traced through a complete seasonal cycle. The prospects for future research are connected, above all, with possible space missions that could enter Uranian orbit or conduct extended observation of its system. Such projects are under discussion in the scientific community, but their realization demands considerable resources and time. Until they are achieved, science will rely on a combination of remote observations, laboratory experiments, and theoretical modeling. As a result, Uranus remains a planet about which enough is known to identify its unique features, but not enough to construct a complete and verified picture. Scientific knowledge in this case is mosaic in character. Individual elements are described with high precision, while gaps remain between them, and these gaps are not a sign of science's weakness, but reflect the real limits of available observation. Uranus appears as a planet in which a multitude of fundamental questions in planetary physics are concentrated. It is simultaneously well characterized in general outline and poorly understood in detail, and it is precisely this combination that makes it an important object for reflection on the nature of planets, the limits of scientific knowledge, and those areas where uncertainty remains an inseparable part of scientific description. Uranus reminds us that planetary systems contain far more diversity than could be expected on the basis of a limited set of examples, and that each new instrument, each new mission, is capable of changing a picture that seems settled. Please leave a comment about how you found this story of Uranus. It matters to me to know whether it resonated with you. When scientists leave Uranus as a planet with open questions, rather than filling in the picture with guesses, does that strike you as an honest position or as a weakness of science? And tell me, do you prefer watching a horizontal video or vertical for your phone?